Today I am here to discuss Module 7 of Unit 4 Alternating Current Electricity. So, before going ahead, I once again tell you that what we have done in previous module. LR circuit, CR circuit, LC circuit, LCR circuits, impedance, LC oscillations, resonance, quality factor, power factor and applications. Now, today we will discuss about to know the power in AC circuit, to explain power and its type in AC circuit, to represent power and its nature in different circuit. Also, we will discuss power factor and AC waveform. Here we also discuss the various application of power in AC circuit. We will explain wattless current and we will also demonstrate the power and its variation. We will solve some conceptual problem as well. So, let us start here. As we know, a whole house energy monitors measures the energy used by appliances connected to house mains. To understand how it does, it is useful to know something about how appliances interact with the electrical system. In previous part of the module, we had the following conclusion as the instantaneous power dissipated in the resistor is P is equal to I square R, which is equal to I square RMS R sin square omega t. The average value of power over a cycle is P is equal to 1 upon 2 I square R. Here I square is I RMS. This RMS current is equivalent to DC current that would produce the same average power loss as the alternating current. Power is an electric circuit is the rate of flow of energy pass in a given point of the circuit. In alternating current circuits, the energy storage elements such as inductor, capacitor may result in a periodic reversals of the direction of energy flow. The portion of the power that averages over a complete cycle of AC waveform that results in net transfer of energy, that is in one direction, which is known as active power. Sometime we call it as real power. The portion of the power due to stored energy which returns to the source in each cycle is known as reactive power. So, we can explain these different type of power like what is active power, reactive power and apparent power. In a simple alternating current circuit consisting of a source and a linear load, both the current and voltage are sinusoidal. That is, if the load is purely resistor, the two quantities reverses their polarity at the same time. At every instant, the product of voltage and current is positive or 0, with the result that the direction of energy flow does not reverses. In this case, only active power is transferred. So, it is active power. If the load are purely reactive, then the voltage and current are 90 degrees out of phase. For half of each cycle, the product of voltage and current is positive, but on the other half of the cycle, the product is negative, which indicating that on the average exactly as much as energy flows towards the load as flows back. That is, there is no net energy flow over one cycle. So, in this case only reactive power flows, there is no net transfer of energy to the load. So, practical loads have resistance, inductance and capacitance. So, both active and reactive power will flow to the real loads. That is why power engineers measures apparent power as the magnitude of the vector sum of active and reactive power. Apparent power is the product of the root mean square of the voltage and current, that is apparent power into account when designing and operating power systems, because though the current associated with reactive power does not work at the load, it heats the conductor or it wastes the energy. Conductors, transformers and generator must be sized to carry the total current, not just the current that does useful to the work. That is, we have another consequences is that adding the apparent power of two loads will not accurately give the total apparent power unless they have the same displacement between current and voltage, that is same power factor. Conventionally, capacitors are considered to generate reactive power and inductors to the consume it. If a capacitor and an inductor are placed in parallel, then the current flowing through the inductor and the capacitor tend to cancel rather than add. This is the fundamental mechanism for controlling the power factor in electric power transmission. So, we can say that capacitors or indicators are inserted in a circuit to partially compensate reactive power consumed by the load. Purely capacitive circuits supply reactive power with the current waveform leading the voltage waveform by the phase of 90 degree, whereas purely inductive circuit absorbs reactive power with the current waveform lagging the voltage waveform by 90 degree. That is, the result of this is the capacitive and inductive circuit element tend to cancel each other. Here we can see this power, how it can be represented in the phase diagram. In this diagram, the power is active, Q is the reactive power, that is in this case it is positive. S is the complex power and the length of S is the apparent power. That is, reactive power does not do any work, so it is represented as the imaginary axis of the vector diagram. So, active power does do work, so it is the real axis. So, here we can say the unit for all forms of power is measured in watt, which is symbolically written as W, and conventionally it is expressed in volt amperes or VA. Since it is the product of RMS voltage and RMS current, the unit of the reactive power is expressed as volt ampere reactive. Since reactive power transfers no net energy to the load, so it is sometimes called wattless power. It does, however, serve an important function in electrical grids, or we can say in transmission center, where from the power transferred to one station to another station. Here we can talk about now what the expression for power and power factor will be. As voltage is written as V is equal to V naught or Vm sin omega t applied to a series LCR circuit derives a current in the circuit, which is given by an equation I is equal to Im sin omega t plus phi, where Im is equal to Vm divided by Z and the phase difference or phi is equal to tan inverse Xc minus XL divided by R. Therefore, the instantaneous power P supplied by the source is P is equal to Vi, as we know. So, we can write it as Vm sin omega t into Im sin omega t plus phi, or we can write it as Vm into Im divided by 2 into cos phi minus cos 2 omega t plus phi. That is, the average power over a cycle is given by the average of the two terms in right hand side of the equation. It is only the second term which is time dependent. Its average is 0, that is the half positive cycle of the cosine cancel with the negative half. Therefore, the power is P is equal to V m into I m divided by 2 cos phi, or it can be written as V m divided by under root 2 into I m divided by under root 2 cos phi, or we can write it as P is equal to V I cos phi. So, this also can be written as P is equal to I square z cos phi, since we know P is equal to I square r. So, we can replace that I as I square. The power factor value measure how much the main efficiency is affected by both phase, say the phase lag phi and it is harmonic content of the input current. Here we can say that the average power dissipated depends not only the voltage and current, but also it depends on the cosine of the phase angle phi, which is between them. The quantity cos phi is called the power factor. Let us discuss the following cases for the power factor. Case 1, resistive circuit. If the circuit contains only pure R, it is called resistive circuit. In that case, phi is equal to 0 and cos phi will be 1. So, there is maximum power dissipation. Case 2, where we have purely inductive or capacitive circuit, if we take the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos phi is equal to 0, that is no power dissipation. Even though a current is flowing in the circuit, this current is sometimes referred as wattless current, and here it is very important, we will discuss this later also. Case 3, we take as LCR circuit. Here power dissipated at an angle phi tan inverse XC minus XL divided by R. So, we can say that phi may be non-zero in LCR circuit or in RL or RC or LCR circuit, anyone. Even in such cases, power is dissipated only through the resistor. If we take another case, power dissipated at resonance in LCR circuit. At resonance, Xc minus XL is equal to 0, that means Xc is equal to XL, that time phi is equal to 0, therefore, cos phi is equal to 1, then the power will be P as equal to I square Z, that is equal to I square R, that is maximum power which is dissipated in the circuit through R, which is the condition for resonance, or it will happen at resonance. We can explain it using a animation also. Here we can see how the power factor, we will show the values of different values of L, C, R, then we can see how this graph look like. Suppose I change the value of R, so you can see this graph how value of IR and IS is changing. If I will increase at the same time inductance value, so how you can see it is increasing. So, the power factor is, we can calculate through these values by changing L, C and R. So, we can have these different values. So, how this power factor is calculated, you can see here. So, by using this different inductance or different reactance values, we can see how the behavior of current, voltage and the power factor is changing. So, now we can discuss here about the power factor. The ratio of active power to apparent power in a circuit is called the power factor. That is, for two systems transmitting the same amount of active power, the system with the lower power factor will have higher circulating currents due to the energy that returns to the source from the energy storage in the load. These higher currents produce higher losses and reduces overall transmission efficiency. A lower power factor circuit will have a higher apparent power and higher losses for the same amount of active power. So, we can say that the power factor is 1 when the voltage and current are in the phase. It is 0 when the current leads or lags the voltage by 90 degree. The power factors are usually stated as leading or lagging to show the sign of the phase angle of current with respect to voltage. That is, voltage is designated as the base to which current angle is compared, meaning that we think of current as either leading or lagging voltage. Where the waveform are purely sinusoidal, the power factor is the cosine of the phase angle phi between current and voltage, that is the sine wave or sinusoidal waveform. The data sheet often abbreviate power factor as cos phi. So, power factor is defined as the ratio of the real power flowing to the load to the apparent power is in the circuit and is a dimensionless number in the closed interval between -1 to +1. Now, here we can take an example. Suppose the active power is 700 watt and the phase angle between voltage and current is 45.6 degree. The power factor is cos 45.6 degree. This value is nearly equal to 0.700. Therefore, the apparent power is then 700 watt divided by cos 45.6 degree and which comes around 1000 VA. For instance, a power factor of 68% or 0.68 means that only 68% of the total current supplied actually doing the work. The remaining amount of 32% is reactive and has to be made up by its utility. Usually, utilities do not charge consumer for the reactive power losses as they do no real work for the consumer. So, for a negative differential resistance is a two terminal electronic component in which an increase in applied voltage across the component result in a decrease for electric current through the component. That is, an electricity meter, electric meter or electrical meter or any energy meter. It is a device that measures the amount of electric energy consumed by the residence or any business house or any electrical device. Electric utilities uses electric meters installed at customers' premises to measure electric energy, which is delivered to their customer for billing or say for billing purpose. They are typically calibrated in the billing units. The most common one being is measured in kilowatt hour or kWh. They are usually read one each billing period or say for the month of the period. So, now here you have a problem, you just answer it. Which of the following two quantities should be multiplied together to find out power? Just for help I can give you answer or option: inductance and capacitance, voltage and inductance, voltage and current, and resistance and capacitance. The right answer is voltage and current. In the same way, we have so many problems based on this module and We will solve them as described in MCQ and problem solving section. What we have learned from this module is all about of power in AC circuit and the variation of power and different type of power in AC circuit, its representation, its behavior, its characteristics in different circuit, power factor, application of power in AC circuit, wattless current and the experimental demonstration to show how this power varies. We also demonstrated some conceptual problem. So, thank you very much, and remember that in next module we will discuss about transformer and its application in daily life.